Kia ora and welcome to the first screencast for data mining at Massey University. So we're going to be looking at workshop 1 today, so I'm going to click through to week 1 and find the workshop, and this opens up a guide for the workshop, and I will read through this obviously in order to know what I'm going to do. If you have not yet installed R and RStudio on your computer, then you can click on this link here under Before We Start to make sure that all the system is up and running for you. Otherwise, we're going to save the lab worksheet for this workshop somewhere on our computer where we remember. So following the instructions, we're going to right click and save the file as, and I'm going to put it in my teaching folder in here, and I'm just going to remember that path there so that I can find it from RStudio. So I'm going to save it there. Then I'm going to jump into RStudio. Here's RStudio, and I'm then going to navigate to that file. So you can see that I'm currently in my 161324 folder, and inside Screencast, inside 2025, I have the first lab sheet. So this is an R Markdown file. It's basically a plain text document with some special highlighting that basically denotes structure. So you can see here that I've got a little bit of stuff at the top here that's describing the title and the type of document that we're going to produce, and then we have some text, and then we have some code blocks as well. Okay, so R Markdown is essentially a way of combining together code in order to do some analysis, and the output from that code, and some plain text in order to tell narrative. So you can see that it suggests that before we start, we knit this document in RStudio, which is referring to this button here called knit. And what this does is it basically creates a new instance of R, a new R session, and runs all of the code that is contained in this file. So you can see here we have some code here in this block here, and then further down we've got some more code and so on. Right. So some of this code is making charts, some of it's doing some data manipulation, and so on. So we're going to start by hitting the knit button, and you can see that it's doing a little bit of stuff down here, some processing, and then eventually it'll be done, and it'll pop up a HTML document or a web document containing the same content. So you can see here that the introduction that we had here with the 2 hashes is larger, so that's a title, and then you can see that various things have been rendered differently. So you see the ggplot2 and the dplyr here are rendered in a different font, and that's because they contain backticks around them. Right, so this is denoting different formatting options. You can see that we've got a bold here, okay, which is done by the 2 asterisks and so on. Okay, so the reason that we knit the document before we start editing it is just to make sure it works, right? So in theory it should work because I've written it and hopefully I know what I'm doing, but it basically gives some confirmation that your system is set up correctly, so that if you then hit any problems with knitting the document, so for example you get an error of some kind, then we know that the error was not in there when you downloaded the document. Therefore, the error must have been introduced by something that you did, which can potentially help you debug that problem. Okay, so now that's done, we're going to figure out what it's doing. So you can see here that we're starting by running the setup block that is loading some packages, and then looking at some data. So you can run each of the code blocks just by hitting the green button there, the play button. And you can see that what that does is it copies the code down to the console window, which is where R is running. So this is the software R programming language that's executing our code. And when we did that, we got some output down here. We didn't get any output up in here, up in the main editor window, but we will later. And the reason we didn't get any up here is because of that setup. So this is called a setup chunk, which is a sort of a special code chunk in that this always runs when you run any of the other code in the file. And what it's done is it's loaded two packages, the tidyverse package and the Palmer Penguins package. The tidyverse package is a suite of packages for doing data analysis in R. Whereas the Palmer Penguins package is basically a data package containing data on some penguins, okay, which we will then be looking at today. So the tidyverse is what we'll be using for all our data manipulation and also our charting. And essentially it is a what's called a meta package. So its job, the tidyverse package's job, is to load other packages. So you can see here the output that it's attaching core tidyverse packages, and it has a list. So we've got a package called dplyr, forcatch, ggplot2, lubridate, per, readr, stringr, tibble, and tidyr. And these are packages that work well together to process data, essentially. So today we'll be using ggplot2 for charting. We'll also be using dplyr for data manipulation. I don't think we're going to be using forcatch. That's for dealing with categorical variables or factors. Today I don't think we're using lubridate, which is for dates and times, or per. We will be using readr to read some data in, and I think we may be using stringr, which is for processing strings, so doing things like subsetting strings and things like that. We won't be using tidyr today, but we will in an upcoming workshop. And tibble is used for basically storing data. So all of the data that we'll be seeing takes the form of a data frame or a sort of an array of data, and the specific data type that we'll be using is a tibble, which is a particular sort of class that implements the data frame functionality. There's also some scary looking conflicts here. So you see we've got some red crosses. So the green ticks, they all look happy, but we've got some conflicts. Okay. Now this is nothing to be concerned about. What it's telling you is that one of these packages, dplyr in particular, contains two functions, filter and lag, that are masking the filter and lag functions from the stats package. So what this means is that dplyr contains a function called filter for filtering data, that's useful, and a function called lag for computing time lags, which again will be useful. But there's also already a function called filter available to R in the stats package. And the stats package is loaded as soon as you load R up. So it's one of the sort of the base packages that always gets loaded. So what this is telling you is that when you type filter, or when you use the command filter, it's going to be using the dplyr version, not the stats version. Or if we use the lag function, it's going to be utilizing the dplyr version rather than the stats version. Okay, so it's not a problem in this case. We're going to be using the filter function today, and we want to use the dplyr one, not the stats one, so that's exactly what we want in this case. But later on in the course, where we will be loading more and more packages, we may end up with conflicts that do make a difference. So sort of a classic one is later on in the semester, we're going to be using the mass package, MASS, to do linear discriminant analysis, which is a classification technique. And the mass package contains a select function. And dplyr, one of the ones that we're loading with the tidyverse here, also contains a select function. And it turns out that when you use select in your code, it is almost certain that you want the dplyr one rather than the mass one. So if you loaded the mass library after loading the tidyverse, it's going to go and set up the select function to point to the mass version rather than the dplyr one, and you might get an odd error when you try and run select, because you think it's going to be the dplyr one, but in fact the mass one takes over. So there's ways to resolve this, obviously. So for example, if you actually type dplyr : filter, then it knows that it's using the filter version from dplyr. Whereas if you type stats : filter, it'll use the stats version, right? So you can always get around it by specifying the name of the package beforehand with the double colon, okay? But if you don't do that, which is quite verbose, and most of the time you don't bother telling it which package is which, then you might possibly have a clash. In this case, the clash is good for us because we want the dplyr version of these functions. Okay. So a little bit further down, we're going to be starting by looking at some charting. Okay, so we have a code block here that is doing a chart with ggplot. So let's run that to see what we get. Okay, and sure enough, we get a chart. Let's have a look at the chart and see what's on it. So we can see that we've got a scatter plot. So this is using the point geometry. So you can see here I've got geom point because we're creating points. And of course, a point geometry needs to know where it's going to get the x and the y from, right? Because each point needs an x coordinate and a y coordinate. It needs to know where on the plane to draw that point. And you can see that it's taking it from flipper length and body mass accordingly. So we have this mapping in here, which is defining the aesthetics of the plot. So aesthetics of the plot are essentially features of the plot, the x and the y coordinate, for example. It might also be the color or the shape or the size of a point or line or something like that. And they need to be mapped to features of the data, right? So features of the data will be columns in your data that define the various x coordinates or y coordinates, right? So there's going to be a column in the penguins data. Let's in fact have a look at the penguins data. If we go to our environment, we'll run the penguins command again, and perhaps that'll, oh, there we go. There's the penguins data. So I just I put my cursor on that and did Control R, which is a short form for run. I could also just press the run button there as well. But using the keyboard is often a little bit quicker. Okay, and you can see that there's columns for the build length, the build depth, the flipper length, and the body mass. So here we're using flipper length and body mass in our chart. Okay, and you can see there's actually been two outputs here. We've got our chart output, but we also have some console output, which is text output. And you can see that it's removed 2 rows containing missing values or values outside the scale range. Okay, and that's because there's two observations in this data set that don't have the flipper length or the body mass, you know, one of the two recorded, and we can possibly see those. Let's have a look. Yeah, here we go. So the 4th observation here doesn't have the flipper length or the build depth recorded for that individual. So presumably that individual wasn't measured, or if it was measured, it was lost before it was noted down. So when we create a chart with ggplot, there's a reasonable amount of writing, but it follows a recipe, right? So we start off by saying that we want a ggplot, and then we provide a data set. So in this case, it's the penguins data set. So the penguins here is the name of the data set associated with that particular data set of data. So we called it penguins because that's the name of it, right? Later on, we'll be using some school roll data that will be readied in. And at that point, we name it whatever we want to. So we create an object and name the object how we like. We then use that name throughout. Right, so that creates a new plot and associates some data with it, and then we add some layers. So in this case, we're adding a point layer. So that's a layer of it's a geometry that describes how the data is going to be represented on our figure. So in this case, we're using points, so it's going to give us a scatter chart, and then we map our x and y to it. And all our ggplots will have that same sort of recipe, right? So use ggplot to create the empty chart, assign some data to it with the data argument to ggplot, choose your geometry layer, and then assign or map the features of the chart to columns in our data via the AES argument, which is short for aesthetics. Now another thing to note is that I've been quite careful in naming all my parameters. So these, so ggplot is a function, so the open parenthesis, close parenthesis are denoting the set of parameters that I'm passing to that function, and all of them have been named, right? So I've said that the data parameter should take the penguins set. Under the geom point, I've said that the mapping parameter to geom point should take the output from this AES function. And within the AES function, I've said that x is assigned to flipper length and y is assigned to body mass. Now, naming parameters is optional. You don't have to do so. If you don't name them, then they will be assigned in the order that the parameters exist in the function. So the ggplot function the first parameter to the ggplot function is the data parameter. So I could rewrite this just by getting rid of the data equals, and it would still run exactly the same. Similarly, the first parameter to geom_point is the mapping parameter. So again, I could get rid of the mapping equals, and the code would run without problem. And again, the first parameter to AES is X, and the second parameter is to AES is Y, so I could also get rid of the X equals and Y equals. So I could write this entire code more succinctly like so. And that would give me the same plot. Okay. Now the disadvantage of doing so, of course, is that now I need to know, right? If I go back and look at this code, I need to understand that the oh, I put X and Y in there. I don't even have to do that, right? Just so used to always naming things that I do it without thinking. But now I need to sort of remember that the first argument to geom_point is the mapping argument, which takes AES, and I have to remember that the first argument to AES is X and the second argument to AES is Y. Now I remember that, but I probably couldn't tell you what the third argument to AES is. I think it's color, but I'm not 100% sure, right? And so my advice would be to name things, even if it means typing a bit more. Okay, simply because it helps sort of self-document what's going on. Okay. Right, so let's do some experimentation. So we're going to add a new code block. I've just typed it out by hand that time, but we're going to need one under 2 and 3 as well. I could, I think it's Control-Alt-I? Yes, Control-Alt-I on my machine. I think it's Command-Apple-I, I think, on a Mac. Have a play around. And that inserts a code chunk, right? You can also do it by clicking this little button here. Oh, there we go. It's even telling me that it's Control-Alt-I. Insert a code chunk. Okay. Okay, and then in this one, I'm going to do a new plot, adding color equals purple, right? So I'm going to be lazy and copy and paste the previous one. Copy and paste being an extremely powerful tool that you should utilize as much as possible. Particularly with your own code. I recommend against copying and pasting code from other people unless they have the correct context. Right, so I've copied and pasted the original code in and I've run it to make sure it works, right? Now I'm going to alter it to add color equals purple as an additional argument to geom_point, right? So here's the geom_point. I've got my mapping argument. So after the mapping argument, I'm going to put a comma to separate the parameters, and I'm going to add a color equals purple. Notice that I put purple in quotes. I could use a single quote or a double quote as long as I'm consistent at each end. Okay, so here I've specified color equals purple, so I expect that my points now will be purple rather than black. And they are. Okay, so this is called setting an aesthetic, where I am specifying one of the features of the plot, in this case the color of the points, to be the same for every point on the plot. Okay, so I haven't mapped the color aesthetic to data because I'm not allowing the color to change by the different rows in the data set. Instead, I am setting it the same for all observations. Notice that I've put it inside the geom_point but outside the AES. Okay, and that's important, as we'll see in the second example. So let's run the same code, but this time I'm going to put the color argument inside the AES. So again, it's already inside the geom_point, but now I'm putting it inside the AES, and we're going to run that and see what happens. So you can see that it runs. I don't get an error, and it has given me a chart where the color is purple, yet it's not, is it? It's actually red. So the points are actually colored red, but I have this handy guide translating that red is equal to purple. So this is probably not what I wanted to achieve, right? Presumably when you ask the color points by the color purple, you don't mean I want you to assign all the points to a group called purple and then produce a chart with the grouping aesthetic being applied. But that is what's happened. So because we've put the color argument inside the AES, it's treating it as if we'd added a new column to the data called color that is filled all the way down by the entry purple. Right? So it's like we've added a new grouping variable that has the same group for all observations. So when ggplot interpreted this to produce the chart, it said, oh, sure enough, you've got a new column called color. It doesn't know that that thing is supposed to be defining the color. All it sees is that we've got a column called color and it's set to a bunch of labels called purple, and so it's colored it by group. And when it colors things by group, it gives us a wee guide telling us what each color that it's used in the chart is maps to which group, right? In this case, we've only got one group called purple, and so it said that the red dots represent the purple group. So that's clearly not what we want. So if you're trying to set an aesthetic for all observations in your data, it needs to go, the parameter for it needs to go inside the geometry, but outside the mapping argument. So outside the AES. Okay. On the other hand, we may want to map the coloring aesthetic to a column of our data. So let's do that. I could copy and paste, but I'm just going to type it out for a bit of practice. So we're going to the mapping argument. So we're going to go flipper length in millimeters for our X, and our Y is going to be our body mass in grams, and our color is now going to map to species. Okay. So now I'm mapping the color feature of the points to the species column, and these data have 3 different species, so you can see that it's colored those 3 different species as separate colors. So we've got the adelies and the chinstraps, which are smaller penguins, so they have a smaller flipper length and a smaller body mass, and then we've got the gentoo penguins that are larger. And so we can see that some of the relationship that we saw on this chart here, where increasing flipper length resulted in larger body mass, which is kind of a natural relationship that you might think of for a bird, right? Larger birds are going to weigh more, probably going to have bigger flippers or bigger wings, you know, if it's a flying bird. But a lot of that relationship is actually being driven by the fact that you've got different species, right? So the relationship is not as strong when you look at the per species relationship. So it's, you know, one of these examples where the initial correlation that you see between 2 variables is actually being driven, at least partly, by something else. Okay, so another thing to notice about this plot is you can see that everything lines up on a grid, all the points, right? So these are continuous measures, flipper length and body mass, yet they've been rounded, right? So you can see that the flipper length has been rounded to the nearest millimeter, and the body mass presumably to the nearest gram. Because of the ranges here, presumably the effect of the rounding on the flipper length is larger than the effect of the rounding on the body mass, assuming body mass has been rounded to the nearest gram, right, just due to scale. The number of significant figures after rounding for body mass is bigger than the number of significant figures for the flipper length. And that's why you see sort of the vertical stripes of points, but you don't see the horizontal stripes as much, although maybe there is some. Okay. So the result of that is that there could be points that are stacked on top of each other that we can't tell, right? So this observation here it could just be one penguin, or it could be 10 penguins with the same flipper length and body mass all stacked up onto each other. We can't tell because we have no depth indication on the chart. And there's two ways that we could look at this. One is we could move the points by jittering them around, add a little bit of random noise to the x and y coordinates of the point so that they all move a little bit away from their true value. And that would help distinguish points if they were stacked on top of each other. Or we could use some transparency so we can see through points, right? And when they're on top of each other, the points will then sort of get darker because you'll see through one and see another one underneath. And so this is these ideas allow the concept of ink density to reveal where there's more data, right? So points that are stacked up will be able to be distinguished. So let's have a look and see how we could do this. We can see that one idea is with jitter. Perhaps before we do, I'm just going to go back up and add a note up in here, right after this block here, about what's going on, right? So when we want to set a okay. Right, so the first idea is to do jitter. So let's perhaps take the original plot without the, well, we can get rid of the purple. We can leave the purple in, doesn't really matter. And what we're going to do is just switch the geom point to geom jitter. So you can see here that when we do that, all of the points no longer line up vertically or horizontally. They've all been, we've moved them all around a bit. So this helps you detect in here, for example, that we've actually got fairly high point density, right? There's actually, maybe 8 or so points all stacked up, whereas perhaps in the original plot, some of those would have been on top of each other, right? And it would have been hard to tell how many points there were. Okay, so that's jittering. We could also use some transparency, which is done via the alpha aesthetic. So alpha is sort of a property of the underlying color, if you like. I mean, we could keep it being purple. Why not? We're going to just add alpha. We'll switch it back to geom point, and we're going to add alpha. And alpha takes a number between 0 and 1. 1 means completely opaque, which is the default. 0 means completely transparent, in which case you won't see anything. And then in between is in between. So we're going to try 0.5, which will sort of be half transparent, if you like. And so you can see that it's made the points a little bit transparent, and you can see then that we get darker observations, darker points where there's overlap. So you can see here that these points here, where we've got a darker look to it. That's where multiple points are stacked on top of each other, because we're seeing through the top one and seeing the one underneath, and perhaps the one underneath that. Okay, and it's lighter everywhere else because there's only one observation there. Okay, and of course you can combine these two things, right? So you could switch that to a jitter as well. So how much you have to do kind of depends on the density of the data. So if you had many millions of penguins, then you definitely want to use a whole heap of transparency and maybe some jitter. Okay, so let's switch to jittering. So you can see that this combines it, so that most of the points have been moved out of the way, but some of them are still overlapping, right? So again, you can pick up indications of density based on the intensity of the colour. Okay. You can also change the amount of jitter. So if we look at the help for geom jitter, to get the help in a quick way, I put the cursor on the geom jitter function and just press F1. That brought up the help, and you can see that there's arguments for width and height in here. And if we see what that says, this is the amount of vertical and horizontal jitter. So the jitter is added in both positive and negative directions. So the total spread is twice the value specified here. So if omitted, it defaults to 40% of the resolution of the data. So we could add width equals, so it'll just be the amount. So if I specify a really big amount, like 10, height equals 0, right? So this is going to give no jittering at all in the Y direction, but it'll give a lot of jittering in the X direction. So you can see here that we've got a lot of jitter this way. So let's compare that to this. Let's run the whole lot maybe. All right, so here's the original one. You can see that the range goes from about 173-ish up to 230-ish, but now that I've added a heap of jitter, it's going all the way down to 163-ish and going well past 230, just because it's moved the points a whole heap. So we've added a lot of random noise to the point where we may have changed a penguin that had flipper length 180 up to maybe 190, or possibly down to 170, depending on the random number generator. So this, of course, is way too much jitter, but it allows you to control it. So for example, if I only did 0.1, then this would only be a small amount of jitter. So you can see they've moved a little bit, but they're still roughly lined up vertically. Okay. So you can define as much as you require. So the default is so that would be 0.4 in this case, because the observations are aligned to the integers. So 40% of 1 is the default used. You can see that in here, right? So defaults to 40% of the resolution of the data. Resolution of the data being the smallest gap between two observations. So the smallest gap between two observations is 1 millimeter. So by default, it's using 0.4 millimeters as the amount to jitter. So, and as soon as you go past 0.5, you potentially get overlap, right? Because an observation at 191 could have been jittered down as far as 189, as 190.5, and an observation at 190 could have been jittered up as far as 190.5. So there's potentially overlap there. Okay, so those two things can be used to help indicate density, particularly when you've got a lot of points. Okay, so currently we've been only using one layer, right? We either used geom point or geom jitter, but we can use multiple layers. So for example, in this code here, we've got both a point layer and a smooth layer. So the smoothing layer is adding a smooth trend to the data. So this is let's have a look to tell us. It's a low S smooth, which is a local linear smoother. So essentially what this is doing is it's fitting a straight line through the data, but it's doing so locally. So it's only considering the points around. So to estimate the slope sort of around 190 millimeters, it's only using points around 190 millimeters to do it. It's not using points way up at 230, or if it is, it's down weighting them, right? So it's sort of a weighted regression, if you've heard of that. If you haven't, treat it as a smooth curve, right? So it's some statistical summary of the data, which in this case is trying to capture the relationship between body mass and flipper length. Okay, and of course we've got the points as well, so it's put one on top of the other. Notice that it's rendered the line, the smooth trend here on top of the points. That's the ordering. So if I change the order, right, and I do the smooth first and then the points afterwards, then the points will be on top, right? So you see that the points are on top. Generally, I think it's probably better to have the data points in the background and the statistical summary on top, but that's up to you. Notice that when we do this, though, we've got some repetition, right? So let's go back to what we had before. Right, so we've got some repetition in that the mapping has been defined twice, and it's identical, isn't it, in both cases. And whenever you have repetition in your code, that has a potential for introducing an error. Like you might accidentally typo, or perhaps you use the wrong variable for y or whatever, and that may introduce faults. And in this case, we can simplify it a little bit by noting that that the ggplot function, as well as having a data parameter, also has a mapping parameter. So you can specify the aesthetics at the plot level, which is then inherited by the different geometry layers that you put on. So this code down here, where I specify the mapping directly in the ggplot function, gives us the same output, but of course it's less typing. Okay, so so another way to do this, which sometimes I prefer, is you can also just add the AES bit directly on. And then do the layers. So this also works. Okay. And this is kind of, in some senses, a little bit nicer because you're kind of breaking down what the code is doing a bit, right? So you're creating a plot and assigning the data. You're then defining the mapping. So you're defining the aesthetics that you're using on the plot, and then you're defining the layers underneath. So any of these forms is fine. Use whichever you prefer. If you don't mind the repetition, do the repetition. It's completely fine, right? Now, of course, we might still want to put the species on here. So we might want to override the mapping in order to supply an additional aesthetic to the point layer, but not to the smoother. So we might want the smoother to be to operate on all of the data, but have the points colored by species, for example. Okay, so let's try that. Right, so maybe let's use this form. Right, so our aesthetics are defined at a global level, or at the plot level, if you like, but then we're going to add an additional argument to the point layer to do color. Right, so now my smoother is exactly the same as it was before. Right, same shape, but the points are coloured by species. So the X and the Y aesthetics are still being taken from the flipper length and body mass for both layers, but the colour's only been defined for the single layer. Okay. So the alternative is to allow the smooth to be affected by the colour as well. Right, so instead of just specifying it for that one layer, we could specify it at the global level so that both layers inherit it, and in that case we'll get 3 different smoothers, right? Because the smooth has to change per species. So what it's doing in this case is it's fitting separate local linear smoothers to the red data, the green data, and the blue data, the different species. And you can see that as a result, each of those smoothers are less smooth, right? And the reason is, of course, is that they're operating on fewer data points, right? The uncertainty bands, so the grey bands here, are wider, again, because we're operating on fewer data points, okay? Which is a fairly natural thing. Notice that the uncertainty at either end is also higher than it is in the middle. And again, that's because you just got fewer data points at the ends than you do in the middle, right? So in the middle, you've got data on either side of the points that are contributing to that statistical summary. Whereas at either end, you've only got the points at the ends that are contributing to the summary. So thus, you have more uncertainty at those points. Okay. So that's scatter plots. What about densities? So what about looking at a single variable, numeric variable, and looking at summarizing the distribution? So obviously we have a histogram, which we can do with geom histogram. Okay, so this of course is dividing the flipper length into separate little buckets or bins, and then counting up the number of penguins that land in each bin. So for example, you look at how many penguins are between, say, 195 and 205, and you just count them, and there's 10 of them, so that's why the bar is 10 high. So you can see that that there's kind of two main humps to this distribution, but there's a bit of noise as well, right? There are other options, so there's densities. Right, so let's take that same code and just switch to a density. Notice we don't need the y aesthetic, of course, because the y aesthetic has been computed, right? In the case of the histogram, we're counting the number of penguins of that particular size, so it's just the count is the y-axis, right? We don't need another variable from our data because we're just using the one. So a density is basically a smooth histogram, right? So you're capturing that signal of those two humps in the shape of the histogram, shape of the density. Okay, so you can treat a density like a smooth version of a histogram. What about adding some color? So what if we want more than just the single variable here? Okay, so we can map the color. So color equals species, say. Try that. Okay, so you can see that color obviously defines the external line of the bins of the histogram, whereas fill is going to be the internal lines of the bins of the histogram. Okay, so fill to fill bars in, color to color the outside of them. So in this case, you'll notice that the shape I get here is exactly the same as the shape I got up here. Right, so the total height of the bars are the total number of penguins with that flipper length. So that means that these bars must be stacked on top of each other, right? In that, so for example, if we look at this bin here, we've only got, I think it's probably just one penguin that's in a dally of that size, and then we've got, say, 4 penguins that are chin straps of that size, and then 15 that are Gentoo penguins of that size. Okay, so all up 19 penguins, right? So the bars are stacked on top of each other. So it's very difficult here to compare the shape between the red and the green and the blue, other than we can kind of tell that the blues are all bigger, right? Because they've got larger flipper lengths, but it's hard to see the shape of the red versus the green. It looks as though the green are a little bit larger, but they've been added on top of each other. So it's harder to see exactly where the peak in the red is, for example, because we've sort of got to infer it by moving all these red bars here down to the baseline. Okay, so we'll look at how to solve that in the next one, or we might as well just do it now while we're onto it. So let's just write these bars stack each other. So only the Gen2s are consistently starting from count equals 0 and going up. The chin straps are starting from the top of the blue bars and the adeles of the chin straps. So it's hard to compare the distributions as each bar doesn't start at count equals 0. Okay, so to fix that you can use the position argument. So let's add our colour fill, isn't it? Okay, so we can use Google to do this, or you can use the help of geom histogram. So if we again press F1 to find the help of geom histogram, then we can see that there's a position argument. So a position adjustment to use on the data for this layer can be used in various ways to prevent overplotting and improve the display. Doesn't actually tell us how to do it, which isn't strongly useful, so maybe we'll Google instead. Histogram, ggplot, start bar at 0. Histogram and ggplot does not start at 0 on the x-axis. That's not quite what we want. That's this way round. We want the other way around. Oops. Histogram with several groups. Let's have a look at this. Okay. So let's see what it's doing. So notice here that we're using position equals identity in order to put them on the same graph. So let's try that. That's better. So they're now starting at the baseline. Okay, our totals aren't the same as what they were before because now they're the totals within groups. So now they've been sort of pasted on each other. So the adeles have been drawn first, then the chin straps have been drawn over the top of them, and the Gen2s over the top of those. So we might also want to add a little bit of transparency in order to see through them. There we go. So now you can see that that there's that overlap, right? We've got this darker green colour, which is the green overlapping with the red. Okay, so now we can actually compare them and see that it does look as though the chin straps are a little bit larger in flipper length on average than the adeles because we've got a shift in distribution. And of course the Gen2s are bigger again. Okay, we can also use the use fill in the densities. So let's have a look at that. Where's our density here? Right, so let's add, so we could use colour. So you can see here that they always start at 0, and so they're coloured differently. With the outside, and again the fill would be the inside. Okay, so sometimes it's useful to use both. Whoops. Right, so we have sort of solid curves without the black outline, and it's useful to use some transparency. Now the transparency, you remember, needs to go in the density rather than in the mapping. So there we go there. So you can easily see that, that the Gentoos are larger than the chin straps, which are larger than the Adelis. Notice that the area under the curves here is the same. So densities are normalized for the sample size, whereas the histograms were not. So the histograms were just doing counts. So for example, the counts on average is lower for the chin straps because there are fewer of them, whereas the densities are such that the area under the curve is always 1, and so the height is therefore scaled based on the on sort of the width, if you like. So the actual numbers here on the y-axis are sort of arbitrary because they depend on the fact that we're measuring these things in millimeters. If we switch them to be measured in meters, then these numbers would all be divided by 1,000. And so in order to make it the area under the curve equal to 1, the y-axis would have to be multiplied by 1,000 in order to everything to balance out. Now, one of the arguments we've got for densities is the adjust argument. So what a density is doing is, so let's run that again. What the density is doing is it's doing a kernel density estimate. So essentially what this is doing is it's smoothing the data by essentially dropping a little blob of jelly, if you like, on each point, and where the points are similar, so where the flipper lengths for multiple penguins of the same species are similar, those blobs of jelly sort of accumulate and you get a big hill, right? So that's why you end up with this sort of shape. But one of the things that you have to do during that process is you have to specify the shape of that jelly that you drop, if you like. Is it a big wide sort of pancake type thing where you basically are saying that you have more uncertainty about the exact value for the flipper length? Or is it a sort of a tall spiky thing where you say you've actually got quite a lot of precision in the flipper length? And that somewhat depends on how much data you have, right? The more data you have, the more confidence you have that sample of data looks like a population, so therefore you can use less smoothing, right? So the density function estimates what it thinks is the best amount of smoothing to apply, but you can adjust it. So for example, you can do so with the adjust parameter, and adjust equals 1 gives you the same thing you already have, right, which is the default. So the adjust function is a multiplier on the amount of smoothing. So if you specify something larger than 1, it will give you more smoothing, and if you specify something smaller than 1, it'll give you less smoothing. So for example, if I specify, say, 0.5, then you can see I've clearly got less smoothing because I get a more sort of noisy plot. And if I specify a number bigger than 1, I get less smoothing, so I get less detail. So there's sort of a sweet spot that trades off the amount of noise you get, which you get when you have an adjust parameter too small. Right, so say we go adjust equals 0.2, right, which is a lot less than 1, so we get a lot of noise. There's a trade-off between that and getting signal. So if I put it too large, then I get essentially no signal, right? It's basically saying that, I mean, if I put it even bigger, so say I put it like at 10, then it's essentially saying that most of these things are roughly the same, right? Maybe there's some difference in the Gentoos, but there's huge amounts of overlap in the distribution of flipper length. So we're getting less signal, right? And as I drop the adjust parameter down, I get more signal, right? More and more signal, so I've got more and more shape information about the distribution. So now I'm picking up this little bump here, right, which might be a small subset of the Gentoos, which are quite a bit larger. There's a little bit of shape here as well, so the spikiness of this one is a bit more than this one maybe. But as I reduce more and more, right, I get potentially more features, but at some point those features become noise. So this is because there's two properties of a statistical estimator that describe how well that estimator does its job of estimating a population thing. So in this case, we're estimating the shape of the distribution of flipper lengths that you observe in the population of penguins. Those two properties of our estimator are bias and variance. So bias is basically, does the estimator give you the correct answer on average? So if you use the estimator across many data sets and average them, do you get the right shape? Variance is how much variation does that estimator have from sample to sample. Okay, so how much does the density, the shape of the densities that we get vary from sample to sample? So it turns out that bias always improves as the adjust number goes down and the sample size goes up, right? So as long as you resample enough times or sample enough individuals, your optimal bandwidth, which is the sort of the width of that or the amount of smoothing, goes to zero, right? And so you basically end up with less bias as you make the adjust parameter go to zero. But the amount of variance you get goes up as the adjust parameter goes down, right? You can sort of imagine this because as the adjust parameter goes down, essentially, you just get a picture of your data. So this is just telling me that I've got a whole heap of penguins that have exactly 190, and then I've got fewer penguins that have exactly 189. All these spikes are spikes because of the rounding, right? And you can clearly see that if I had a different sample, so I go out and collect a bunch of other penguins, other Adelie penguins, that I'm going to get different individuals, right? And so those spikes are going to move a whole heap. And so the sample to sample variation there is going to be very high. But if I averaged across those samples, I would very accurately capture the population truth because of the averaging process. So if I reduce the adjust parameter, I start eliminating bias, but I increase variance. On the other hand, if I increase the adjust parameter, so I start going above 1, right, so let's go to 2, right, then the variance is going to be lower, right? If I get a new sample, because I'm smoothing a heap, the shape of the density that I get from that new sample is going to look a lot like the shape of the density I get here because I've just smoothed it heaps. So the variance drops right back, but now the actual shapes that I'm getting don't look like the population anymore, right? Because I've over smoothed things, so they no longer are capturing the truth. Even when I average across them, I'm just averaging across a bunch of blobs none of the blobs are a good picture of the population. Therefore, the average of them is also not a good picture of the population either. So by increasing the adjust parameter, I increase my bias because the shape of my densities don't look like the population anymore, but I decrease the variance, right? From sample to sample, I get the same shape. So these two things, bias and variance, are always trading off against each other. And it turns out that there is sort of an optimal value for the adjust, which in this case is 1, right? So the density estimator is trying to balance the bias and the variance. And we're going to see this over and over in this course, that we'll be constantly trying to balance bias and variance. And sometimes we might choose a model, for example, in prediction or something, that we know has a bit of bias in it, just because we know it will also have less variance. Other times we might want to choose a model where we're allowing a bit more variance because we know that it's unbiased. Okay, so there's always this trade-off that we'll be undertaking. Okay, and I guess the last thing we're going to do is just remind ourselves how we change to box plots, which I missed, sorry. Let's do that here. Let's also write a little bit about the bias variance trade-off. So small values of adjust, introduce noise, Okay, so just a note that this can be a bit of an art. While there are some, a bunch of mathematics that basically tell us that adjust equals 1 should sort of on average give the best answer, for a particular data set you may find that playing around with the adjust a little bit, not too far, I wouldn't go sort of more than about 1.5 or less than 2/3 I think, may help smooth out any irregularities or focus in on the key signal. So we should also do a box plot. All right. So there's a box plot. So fill is filling in the inside of the box plot. Color's doing the outside. Let's just do the outside maybe. So there we go. There's the box plot. You can see that because the box plot essentially is one-dimensional, right? The only thing that matters is the what is happening horizontally in this case. The vertical height of the box or anything is meaningless. So this scale over here is completely meaningless. Because of that, you can utilize the Y aesthetic for something else. So for example, we could make Y equal to the species. In which case we have, our color guide is not really needed, right? So for example, we could turn the color guide off. I mean, we may still want to color them because that looks kind of neat, but we could turn them off by saying color equals none. I think that's how you do it. There we go, and that's turned that guide off because it's not needed, and therefore we've got more space for the chart. Okay, so the advantage of box plots is that while they give you less information, in that you can only tell that half the data are between the boxes, is sort of within the box, so you lose some shape information here compared to the density. But the box plot's really, really good for comparing lots and lots of groups. Okay, you can imagine that the density curves we've got here works pretty well in this case. We've only got 3, and there's enough separation between them that we can kind of see something going on, right? But if, for example, we had 7 groups and they were all plastered on top of each other, it might be a very messy display, right? Whereas the box plot would still be clean, right? Even if they overlap a whole heap, you can still see how the groups potentially differ, because you can stack up essentially as many of these box plots as you like. Okay, so the last thing is just look at labeling. So perhaps we'll just do this density one here. So let's grab that. All right, and we use the labs argument. Okay, so you can add labels for the x-axis, labels for the y-axis. Right, that'll look a bit nicer. Okay, we could add a label for the color. So this is the fill, isn't it? Or fill. So now we can see the downside of using both fill and color is that it's not going to combine these two guides together. So let's maybe just get rid of the color aspect. So we only have the one scale. I mean, we could change the we could make the black line transparent if we wanted to. What else could we go? We could add a title. Gene 2 penguins are larger than Adelie chinstraps. Right, and so on. Okay, we could add maybe a caption. Okay, stuff like that. Okay, so feel free to play around. Obviously, you know, a good practice is always label your charts, right? Take some time to explain to your reader what is going on your chart.